Okay, we'll start, ma'am. Am
Yeah.
I audible?
Yes, yes, absolutely.
Okay. So, we would like to begin with the afternoon session on the fourth day of our Atal FDP program. I would like to extend a very warm welcome to one and all present over here. Dr. Kiran Jatar Madam, our Principal Madam, Dr. Urmila Joshi, the chairperson for this session, Dr. Archana Gurjar, and last but not the least, our Atal FDP coordinator, Dr. Mrinal Sanay. So the first two sessions were highly enlightening and they were quite refreshing for us. And now we have another session on green chemistry by Dr. Kiran Jatar. So I would request the chairperson, Dr. Archana Gurjar, Assistant Professor, Department of Pharmaceutical Chemistry, Principal K.M. Kunnani College of Pharmacy, to introduce Dr. Kiran Jatar to all of us. Over to you, madam.
Thank you, Miss Hina, for. I am really honored to introduce resource person of this session, Dr. Kiran R. Jathar, Madam. She has pursued her PhD in organic chemistry from Institute of Science, Mumbai. She is currently working as Associate Professor and Vice Principal at RD National College, Bandra. She is a recognized guide in chemistry and member Board of Studies in Chemistry for University of Mumbai. She has co-authored two books for undergraduate chemistry, students of University of Mumbai, and book for NEET entrance examination. Her area of research are heterocyclic chemistry and green chemistry. She has many awards and accolades to her credit. To name a few, 100 Most Impactful Global Leaders for the Healthcare and Mental Wellbeing Award by ET Now. For outstanding contribution in green chemistry and education by Pharmaceutical Royal International Society Prisal. Golden Global Award to Green Chemistry Awareness. Eminent Teacher Award by Dr. Roche Global Solutions and the International Women Achievers Award at Dubai. She is an eminent resource person. She has delivered talks at international, national, webinars, conferences, and seminars. Some few glimpses to mention. Keynote speaker at state level seminar teaching an industrial field. Resource person at international webinar on NMR spectroscopy and its applications. Another resource person at new technologies in API manufacturing at BioLeague at Jakarta. And she has delivered lecture on misuse of antibiotics at international conference in Dubai. She has coordinated number of conferences in collaboration with Green Chemistry Foundation, and she's an active member of many academic and professional bodies. So, with this few words, I would like to, we are all eager to hear from you talk, madam. So, the session is yours. It's open for the discussion. Thank you,
Thank you,
madam.
madam. Thank you very much for this kind introduction, and I would like to thank the organizers for inviting me for this lecture. So I'm come to know that today you all have been, already pumped in too much of green chemistry. But let me see. Hopefully, you'll learn something else, maybe something new. So I'll just share my screen. You see the screen?
No, ma'am, yet it is not shared.
One minute. What happened here? Yeah. Can you see it?
Yeah, ma'am.
Yeah.
Share.
Okay.
Just in
Thank you.
the presentation mode, you have to
Yeah,
put.
I'll just put it in the presentation. Okay.
Thank you, ma'am. It's
Yeah.
okay.
So the topic for today is applications of green procedures in synthetic chemistry. Let's see how this particular today's lecture will be. The structure of the FDP will be what is sustainability, fundamentals of chemistry, how they are important to us, reimagining chemistry, green chemistry, some practical examples of green chemistry, and an overview of different aspects of sustainability. So let's first understand the meaning of the word sustainability. We all talk about, a lot about these words: sustainable, global warming, climate change, and then when you exactly ask somebody to define or to explain what exactly it is, we're all out of words. Today, sustainability is something which has to be always there. Today, tomorrow, maybe it was always there in the past, as well as it has to be in the future. So it's a domain of life which is ongoing. And in the 21st century, it is referred generally to the capacity for Earth's biosphere and human civilization to coexist. The Earth's biosphere and the human civilization have always coexisted, but today there are questions whether they can coexist or they cannot, because of the man-made disasters, because of the industrial revolution, because of man playing with the ecosystem, and so on and so forth. And therefore, the need for a sustainable society is very, very important. When we say chemistry, I do not mean by chemistry which we learn in the class, because everything in this life starts with an atom. Everything on this earth starts with an atom. From an atom we get a molecule. From a molecule then we get the nomenclature. And then there are chemical reactions, there is chemical synthesis. You see life, whether it is marine life or it's plant life or it's animal life, everything what we see in fundamentals of chemistry is there. Atoms, molecules, nomenclature, we name them when they convert into molecules. When life comes into it, it is a chemical reaction which is taking place. Biochemistry in your body, in plants, in herbs, in animals, in marine life, everywhere, chemical reactions, chemical synthesis is taking place. And then there is energy and thermodynamics. As I know that all of you come from the field of pharmacy, you know how important it is to understand the energy and the thermodynamics of a drug when it enters into your body. And that is only possible if you know about atoms and molecules. And therefore, chemistry becomes, whenever we say it's the chemistry of life. And therefore, the fundamentals of chemistry are very, very important to us. All of you know what are atoms and molecules and what do you mean by a chemical reaction. You feel hot, you feel cold, why do you shiver and why do you sweat? They're all reactions happening in your body. And they are all the fundamental reactions in our body at any given point of time. We all respire. So a lot of oxidation reaction takes place, a lot of reduction reactions. We get free radicals in our body. So aging is a process because of free radicals and so on and so forth. So how you can relate chemistry to life is very, very important. So let's reimagine chemistry. When we talk chemistry, what we think, the first thing which comes to our mind, it is polluting. It is polluting. Yes, it is. All of us know that. Chemicals are toxic. Even the drugs are toxic. They have side effects. They have adverse effects. But it all depends on the dose and the response. How much is bioavailable to us? And what is the element of risk involved? Life and risk coexist. If there is life, there is risk. If there is no risk, there is no life, is what I feel. And I'm sure all of you will agree to that. The same medicine in a proper dosage form and in a proper dose is a boon to us. But if it is taken in excess, a little more, an extra dose, then it can lead to toxic effects and even may lead to death. So let's reimagine chemistry by understanding the basis of risk and the elements, how much, what dose is there, what will be our response to it, and how we can do it. That means if our body can exist like this, even the earth, if we are not going to, throw everything into the earth, the garbage, the landfills, the pollutants, the waste which we produce in the industry, the e-waste, the chemical waste, your home waste, domestic waste, everything goes into either the landfills or the water, the sewage. So if the dose which is given to the earth is also in proper way, is proper and is calculated, then I think the response will be proper and will not be what is happening today. And that is what is sustainability. And therefore we have to reimagine chemistry so that we can curb on all these things. To do that, we have the greatest tool which has been given to us by the chemists. It has been 25 years from when this 12 principles of green chemistry came into existence. And they are doing wonders. And I hope in the next 25 years, we'll have a green earth and a green chemistry in chemical industry, which will not be blamed for polluting the environment, which will not be. See, there are positive points and there are negative points. There are 80% positive points of a chemical industry and maybe 20% points which are negative. But it's human nature that we look only after the negative part and we don't usually see the positive part. Today, if I tell you, no, the chemical industry is polluting, stop it. Can we do it? No. It is impossible to stop the development because that's what we are used to. That's the life we are used to. So in 1994, the 12 principles of green chemistry came into picture. And by using these 12 principles of green chemistry, the chemists are trying to bring sustainability into the system, into the environment, into the atmosphere. It talks about feedstocks. It talks about chemical synthesis and manufacturing, solvents, catalysis, product designs, accidents, and end-of-life considerations. Feedstocks, that means the starting material which we are using. Are we using fossil fuels or are we using non-renewable resources? Can we use renewable resources for chemical synthesis and manufacturing? The same product which are already existing. Can we change the chemical synthesis? Can we put in or bring in some new chemical reactions or maybe a catalyst? Can we do solvent-free synthesis? Can we design a product which has no side effects or maybe no waste produced? Can we not use hazardous chemicals? and avoid accidents which occur in these chemical industry. And at the end, when the product life is over, finished, what happens to the product? Where does it go? Can we recycle it? Can we convert it into something new, or it goes into the landfills? Very, very important to think about all this. Practical examples of green chemistry. I'll be dealing with certain practical examples on atom economy, green synthetic matrices, chemical property estimations and modeling, toxicity data sources, life cycle analysis, mass balance stoichiometry. So these are some of the points which are very important from the point of view of green chemistry. And we'll see it in the further slides, the meaning of these simple words. So what is green chemistry? What is the future of green chemistry? Are the obvious questions which will arise. 25 years of progress in green chemistry. What has happened in the last 25 years? Chemical plant disasters, can they be avoided? All of us know about the famous Bhopal gas tragedy, one of the worst chemical accidents or disasters which happened in the year 1984 on the night of 2nd and 3rd of December. An estimated 4,000 people were killed, but it is said that more than 16,000 people were killed, and non-fatal accidents were more than 5 lakhs, which is a huge number. So can such disasters be avoided, because they have a very long lasting effect? Then we'll also look into some pharmaceutical, cosmetics, cleaners, agriculture chemicals, energy system, case studies and examples. So this will be the outline of today's lecture. Let's start with green chemistry, reimagining chemistry. So what we have to understand here is, what is green chemistry? Why is it necessary? Why is it necessary? And what are the things which are driving green chemistry? And it has been now being used for last 25 years and still being used and talked about a lot. And what is the future of green chemistry? This is the photograph of the two great scientists, Dr. Paul Anastas, the father of green chemistry, and Dr. John Werner, the co-founder of green chemistry. They have coined the 12 principles of green chemistry. Dr. Paul Anastas is a chemist, and he has coined the 12 principles of green chemistry. And Dr. John Werner has coined the 12 principles of green engineering, because chemical engineering and the chemistry go hand in hand. According to Paul Anastas, the father of green chemistry is the design and synthesis of chemical products and processes that reduce or eliminate the use and generation of hazardous substances in the design, manufacture, application of chemical products. And what Dr. John Werner says is, it's a revolutionary approach to the way the products are made. It's not just the design and synthesis, but it's a revolution in chemistry. It's a science that aims to reduce or eliminate the use and or generation of hazardous substances in the design phase of material development. In the designing of the chemical product, if you eliminate the use of hazardous substances, or you eliminate high energy and number of steps, etc., and come to the same product at ambient temperatures and ambient pressures like nature does, all our reactions, whether they are within our body or whether they are in the plants or in the marine life, they take place at ambient temperatures and ambient pressures, no extra pressure, no hardcore catalysts like vanadium, palladium, those are toxic in nature, nothing. Our body uses catalysts, copper is used, magnesium is used in plants, photosynthesis. Iron is used, so can we use those catalysts? Can we look at nature and then revolutionize our chemistry so that the problem which has arisen due to the Industrial Revolution during the 1950s to the 1980s would not persist anymore. The mission of green chemistry is to promote innovation, clean chemical technologies that reduce or eliminate the use of generation of hazardous substances in the design, manufacture and use of chemical products. Why it is green chemistry and not green geology and green astronomy and any other subject as green? Because chemistry is the science that introduces new substances into the world, and we have a responsibility for their impact in the world. This is what Ronald Breslow told, and I quote it. It's a very important statement. We have a responsibility for the impact of these chemicals in the world, because the chemists are the one who are basically manufacturing or who are basically designing these chemicals, and therefore green chemistry is very, very important, because we need to design chemical technologies which will not generate hazardous substances and they will not pollute the atmosphere. So why do we need green chemistry? It is undeniably a very prominent chemistry is a very prominent part of our lives, of our daily lives, right from the toothpaste and the toothbrush which we use in the morning when we get up to when we sleep, name it, and everything from your pens to your clothes, to your bags, your credit cards, the polythene which you use, the cooking utensils, to the gas and everything. Name it and everything is chemistry. So it's undeniably a very important and prominent part of our lives. Chemical development also brings new problems, and harmful unaffected side effects are seen, which we are all seeing now. And therefore, the need for greener chemical products, the products which are not going to harm the environment. Let's take an example of DDT, dichloro, diphenyl, trichloroethane. Green chemistry looks at pollutants prevention on the molecular scale, as it is an extremely important area of chemistry due to the importance of chemistry in our world today and the implications it can show on the environment. And therefore, green chemistry is very, very important, and this environment friendly chemicals can be achieved by using the 12 principles of green chemistry, which we are going to see later in this PPT. The 12 principles of green chemistry. This is the first book which was authored by Dr. Paul Anastas and Dr. John Warner, Green Chemistry Theory and Practical, which mentions the 12 principles of green chemistry. So the first is waste prevention, atom economy, less hazardous. I'm sure all of you know all these 12 principles because you must have heard about it a number of times, and some of the courses also have them in their syllabus, but they are very important, and it's very important to understand why and how these principles were coined. In 25 years of green chemistry, the principal addresses, what have been addressed by green chemistry is toxicity, reducing the hazard. They've been successful in doing that, but not to a very large extent, because awareness about green chemistry in the last 25 years have taken time to get people aware of what is green chemistry. And I'm sure in the next decade or so, the results, good results will come out. There are many results which are already there, but more better results will come out in the next decade. Feedstocks, that is use of renewable resources, and many chemicals, they have been, I mean, the renewable resources have now been used instead of the non-renewable resources. Then non-toxic products by design. So designing of products which are non-toxic in nature, they are biodegradable, so that at the end of life they can biodegrade and then not cause no harm to the earth. Reduce the energy needs, eliminate accidents and short processes. This is what is done in the last 25 years, and this is what is basically addressed by the 12 principles of green chemistry. So Royal Society of Chemistry, the website is here, has given this 25 years of green chemistry and environment. It's a very good paper if you want to read it. Now let's see that if you want to build a home, you know, you are a builder and you want to develop new homes, what are the building criteria? What is important? The building criteria that the foundation should be solid. Why? Because if the foundation is solid, then safe homes, the homes which will be made will be safe. Like, you know, if we have a solid foundation of chemistry, then what we are going to do and how we can change the reaction, we can manipulate the chemical bonds, and that all of us know we can do it. But for that, our foundation has to be strong. We should know what are chemical bonds, we should know how they can be developed, what are functional group interconversions, how one functional group can be converted in the, what is retrosynthesis, go to the final molecule and then come back to the starting material by breaking it down, and so on and so forth. What solvents can be replaced? Why are you using these solvents? What happens if your compound is a non-polar compound and you use a polar solvent? What do you mean by neighboring group participation, etc., etc. So all these foundations, if this foundation is clear to you, then obviously you can develop a very strong chemical reaction. You can manipulate, you can play, you can design. Okay, so you can be a good designer, but for that you have to be thorough. So the first thing you need is a solid foundation. Second thing is, as much as material you buy, you have to use it. Because if you're not going to use the material you have purchased to build the house, is going to be wasted. So prevent waste. The material which you are going to use, prevent waste. Don't buy anything which is not required, and don't use anything which is going to be a waste later on. So use something which is going to be in the house, and hence the material which you're going to use should not go to waste, but be there throughout the life of the building. Then slope gradient. That means guide water away from foundation. That is accident prevention, because if there is water which is going into the foundation, it's going to make the foundation weak. Similarly, for a chemical reaction also, to avoid accidents, to prevent accidents, we need a slope gradient. We need to know that the energetics of the reaction, we need to know how it is going to be reached, whether we can control the reaction or we cannot control the reaction, What changes can we make to control the reaction, and so on and so forth. Like if water is going into the foundation, we know that it's going to rust the iron rods which are there down, and then it is going to cause corrosion. Similarly, even in your reaction, if you know that something is going to may cause a problem, then you should have a slope gradient. You should know what to do and what not to do. Then you should have natural light, so more efficient. Energy efficiency should be there in your house. We think of all this when we build a house. So the windows should be placed, more on the west, more on the east, depending on which side your house is facing, and how much light. Every room should get light, and so on and so forth, so that you can use optimum natural light and minimum of the other light or the electricity. Similarly, in our own reactions, in our own house, in our own reactions also, we can save energy by using, reactions, or using the certain techniques that will minimize the energy efficiency of the reaction. So you have an optimized floor plan, which is economical, that is at an. So whatever you have in the starting, you have used everything in the product. So whatever you purchase for making your house, everything goes into the house and nothing goes as waste. That's atom economy. Your starting material, everything is incorporated in the product. So to design a safe molecule, you should have a floor plan, and you should use the 12 principles of green chemistry. The first principle being prevent waste. So you start with prevention of waste, not to produce waste at all. Second, maximize atom economy. Third, less hazardous chemical synthesis, safe chemicals and products. So as we go on further, we will take one principle at a time, and then we'll do a case study on that. Why green chemistry is so important? We all know DDT is banned. It's an environmental pollutant. But during the Second World War, it was used on the soldiers. Why it was used on the soldiers? Because they sprayed the soldiers with DDT to control malaria, typhus, body lice, and plague. Farmers used to use DDT on a variety of food crops worldwide, and DDT was also used in buildings for pest control. So extensive use of DDT was observed during the Second World War and after that, till the 1960s. So this is a picture of the aerial delivery to protect the forest against harmful insects. In 1960s, there was evidence of environmental and toxicological effects of DDT. And in 1972, 12 years after that, the EPA issued cancellation orders that DDT cannot be used. And the reasons were: exposure to DDT leads to reproductive effects in human that was suspected. DDT is called as a persistent organic pollutant, the dirty dozen. There are 12. So DDT is one of them. DDT was cancelled because it persists in the environment, accumulates in the fatty tissues, and cause adverse health effects on wildlife. In addition, resistance occurs in some insects like the housefly. DDT is currently classified as a probable carcinogenic, and half-life of DDT is approximately 15 years. So you can imagine, if you spray DDT, it will be there in the soil, in the atmosphere for how long? Because its half-life is 15 years. So DDT was discontinued. Its concentration now, after so many years, 1972 to now, nearly 50 years, its concentration in the environment and animals has decreased. It's still not gone. It is decreased. However, because of its persistence in the environment, DDT degraded residues from with the remains, all remains. You can imagine that what harm it would have caused to people on whom this DDT was sprayed during the Second World War, the soldiers. Then comes the Bhopal gas disaster. As I already told you, that methyl isocyanate was a gas which leaked from Union Carbide India Limited plant. Approximately 4,000 people died, but it is claimed that more than 16,000 people died, and non-fatal injuries at least were more than 5.5 lakhs. Today also there are effects of Bhopal disaster seen in Bhopal. So that was one of the worst chemical disaster which was seen. All this release of greenhouse gases and global warming, we listen and we've heard about all these things a lot. A lot of these things we hear. And methane is there, then combustion, global gases, carbon dioxide, glaciers melting, sea level rising, everything, deforestation, etc., etc. So green chemistry is the need of the hour. Let's see some facts. What are the factors which are involved in global warming? Global green gas emissions, you can see electricity and heat production is 25%. Agriculture, forestry and other land use is 24%. This is the emission of greenhouse gases which take place. Buildings, etc. 6%, transportation 14%, industry 21% and other energies 10%. Now you can see this that electricity, how much of greenhouse gases it is given on, more than the industry. Only production of electricity, and we use electricity in cities like the malls run 24 hours of electricity is used, and we don't bother, we leave our room and go out and do not off the light and the fan is running, and we don't take care of these small things, but obviously they all add to our carbon footprints. This is the temperature rise from 1815 to 1900. If you see, there was hardly any temperature rise. But after 1960 until today, you see there is a temperature rise of 1.2 degrees. So, which is not very good, and it is predicted in the next 10 years, it's going to be 1.5 degrees temperature rise. And if the temperature rises by 1.5, obviously there is going to be a climate change, more floods, etc., etc. And this is happening because of the carbon dioxide emission. The annual average carbon dioxide concentration is increasing year on year. The when we started, if you look at this map in the 1760s, the amount of, that is in the pre-industrial period, the amount of carbon dioxide was just 278 parts per million. And it increased, and by 1986 it increased by 25%, and it went to around 350 parts per million. And now in the next 25 years, from 1986 onwards till today, there is a 40% increase. Can you see, from 2011 to 25 years, that is by 2011, 25 years later, after 1986, it has increased by 40%. And recently it has gone to 50%, and the amount of carbon dioxide in the atmosphere is 417 parts per million. This is observed more in the autumn and winter and less in the during May to September, because the season also counts a lot about the carbon dioxide. So it has crossed the limits, because the maximum limit, which according to James Henson, who is a scientist and who works with this carbon dioxide emissions, The maximum limit which the Earth's surface can accommodate is 350 parts per million, and we have already reached 417 parts per million. In spite of doing so many efforts in the last 25 years, we still reach 417 parts per million of carbon dioxide, which is absolutely not good for us and the planet Earth. So this is also like how we can reduce the carbon emissions, some data about how you can reduce the carbon emissions. Then we come to depleting resources. Our resources are depleting. Why? The population is increasing and we are all using the renewable resources like the fossil fuels. We have the deforestation, natural resources are being depleted at an unsustainable rate, and the solution is green chemistry, as it is about shifting roles, changing education of chemists, understanding intrinsic hazards, design so that we use renewable sources, increasing efficiency, reducing cost, enhancing performance, and doing innovations. So green chemistry can bring a paradigm shift in the role of chemist, using the principles of green chemistry and bringing in synthesis of new products to be launched in various sectors. And that is why green chemistry is very, very important, because the greenhouse gases, especially carbon dioxide, which is necessary to keep the Earth's atmosphere warm, and it is necessary for life, is cross the dangerous mark today, and it is increasing. So if we don't take care, we are going to lose our precious Earth. So what is green chemistry? It's a key to environment and economy, both. Because when we talk industry, we talk about economy, we talk about money, and everybody, the whole industry is making money, but at what cost? So green chemistry is the key to environment and economy, both. Let's see how. Past and present state to environmental problems: waste treatment, waste control, waste disposal. This is our biggest problem: waste treatment, waste control, and waste disposal. Where do it go? Where does the waste go? Either it goes in landfills, or in the air, or in the water bodies. So now, if we don't produce waste, or we treat waste so that the water bodies do not get contaminated, or we can control the waste, then the disposal will become very, very minimum disposal is done, and the problem will be solved. Because now what is happening? All the plastic waste is going to the landfills. It's going in the sea and it's causing a lot of problems, hundreds of problems. This photograph you can see is of the Mithi River restoration. Mithi River, which was once upon time a river which flows in Mumbai, and now it looks like a nala. Many of you must have seen this in Bandra and Mahim. When you cross by train, it goes over the Mithi River between Bandra and Mahim station. It's not a nala, it's a river, a proper river. But dye industry in Ambernath has really created havoc in this river, and it looks like a nala today. And restoration of Mithi River is what is happening today. So let's see at the top 10 polluting industries in the world, past and present state of environmental problems and today's industry. You can see first is the use lead acid batteries. Lead acid batteries are used where? Acid batteries are used where? They're used in the cars. Okay, all transport vehicles. So, disability adjusted life years. People who are working with this is the disability adjusted life years. You can imagine that how much it can cost the people. Mining and ore processing. lead smelting, tanneries, that is leather industry, arsenals and small-scale gold minings, industrial dump sites, industrial estates, chemical manufacturing, product manufacturing, and dye industry. These are the most 10 polluting industries in the world. You can see this. This is acid batteries. Where they go once they are used up? Where they are put up? They are put in the soil, and the soil turns acidic. And even lead is a heavy metal which causes lead poisoning. So you can imagine what will happen. Mining and ore. See this. See, you can see the color of the water. It's a river. It's very close to a mining site. Lead smelting. So you can see what is happening in the atmosphere. So much of lead is getting evaporated. Then you have these tanneries, where leather is, this is leather, you know, people staying very close to this. A lot of acid is used here. Gold mines, these are gold mines, and this is a lake where from the gold mines, this is in Africa. Okay, and this is the industrial site where all the garbage, industrial garbage has been put up. So you can see how we are polluting our earth very badly. So treat aqueous water discharge and effluents before you throw it into the water bodies or into the landfills. Waste transported to be properly disposed. Other mechanisms to deal with end of pipe problems is continuous pollution monitoring should be done in the industry, because if it is not done, we do not know what are the levels and what are we throwing into the environment, whether it is air, water or land. Then hazardous waste cleanup should also be done. Development of standards to curb environmental problems, air emission standards, release standards to water sources, land disposal standards, they should all be highly regulated. And the regulatory bodies should be very, very strict in monitoring these things. Now, if we don't do this, if we produce waste, then and we use hazardous material, then it will cost the industry, because storage will be a problem. Hazardous materials have to be stored properly. Transportation is a problem. If something happens, treatment is a problem. Disposal is a problem. Regulatory cost is very high. Liabilities are very high. Worker health and safety, again, you have to give something or you have to keep certain amount for workers' health and safety. Corporate reputations, community relationships, new employee recruitment, everything will cost you. And in industry, they want minimum cost and maximum advantage. So if we are not going to use hazardous material, or if you are not going to produce hazardous material, then obviously all these things go down. And when all these things will go down, all these points, then obviously the money packet will go up. And that is what is required. Okay, otherwise treating the waste is more costlier than treating the product. It should not happen that way. How are things done now? Currently, entire industries are geared towards cleaning up after wasteful chemical synthesis. That's what they do. They do a wasteful chemical synthesis and then they want to clean it. Today's scientific literature is filled with synthetic pathways that are inefficient in terms of design. Reagents are seldom selected with regards to hazard. Okay, this reagent can be used. Okay, we'll use it. We don't think what is the, what is going to be the outcome, how we are going to, at the end of the product, what are we going to do? Industrial chemicals do not have minimal hazards as a performance creation. Persistence of chemical in the biosphere in our body is a major global health issue. 250 chemicals are still present since 1945 in our body. In the atmosphere, there are still 250 chemicals which are present, which have polluted the earth so badly. A vast task of organic chemicals are made by depleting, majority of them are made by depletion, that is non-renewable feedstocks. And our chemical industry deals with safety through engineering and security through barricades. How can this be changed? The use of green chemistry shifts to the focus from end of pipe mitigation approach to hazardous waste and materials to innovative approaches that address hazards and waste at the source. In the design phase of the product life cycle, green chemistry is applicable across industry sectors and product areas. The future of chemical market henceforth is green, because green chemistry is the only chemistry which is going to help them. So which are the industrial sectors? You can see that nearly everything is covered here, right from defense and aerospace to automotive to specialty chemicals, pharmaceuticals, electronics, cosmetics, agriculture, household cleaners, academia, because we also use a lot of chemicals. When we teach our students, maybe in a very small amount, not as much as the industry, but we do use, and the number of colleges is huge where the chemicals are used. In every field, whether it's a chemistry lab or a bio lab or a biotechnology lab, these chemicals are used, and therefore various sectors green chemistry can be used. Let's take a case study of waste to value adding resources. We all know that the dye industry is a booming industry, and India is the manufacturer of dye intermediates, and maximum of dye intermediates are exported because the process is very carcinogenic. We use beta naphthol, we use alpha naphthol, different naphthals are used, and many of them are carcinogenic, and therefore most of the Western countries it is banned, and then India is the hub where these intermediates are made and they are then exported. Huge money. The first dye, Movin or Mauve, was discovered by William Perkin in 1956, way back. And then it was followed by, you know, a number of dyes like the fuchsin, the Manchester brown, the metallic yellow, etc., etc. And then at that time, the market for natural dyes collapsed. Why? Because natural dyes were very, very costly and very few colors, and you know, the purple color, the indigo dye, which was a natural dye, was called as the royals dye, and only royals could use, and the normal, people could not use. And so this synthetic dyes got a revolution in the market. In 1956, new colors came into the market. In mid 20th century, fade-resistant dyes came into the market. In 56, reactive dyes for textiles came into the market, and then in 1970s, thermochromic dyes came. And the whole industry is now booming with dyes, and you have, different shades of the same color and all. Everything is chemistry. Everything is synthetic chemistry. Organic pigments. Now we'll see the innovation in dyes. So organic pigments have found huge use in high technology industries like the optoelectronic displays and optical data storage and photo reprography. These are some of the electronic companies, optical companies, where dyes are used. But it is observed that the pigments or the dyes which we used, from the perspective of recycling, chemical currents and cost, they are environmentally damaging. You've seen what has happened to the Mithi River. Their insufficient resolution and lack of durability invariably limits their practical application in display and imaging. And to overcome these limitations, a lot of work was put onto structural colors, which are an interference phenomena between incident light and the structure. No dye is used. Absolutely no. Now, for example, you see the peacock. It has got vibrant colors in its feathers. Now, these colors have no dyes in it, but it still has the colors which you see. So how are those colors coming? From where those colors come? If there are no dyes in it, then what is making it colorful? And the answer is the structure of the wing. Same thing is with butterflies. They do not have any dye in it. Structural colors are present everywhere in nature and in daily life, such as in beetles, pollina flowers, peacocks, hummingbirds, morpho butterflies, and so on and so forth. So now let us see this structural color. It's called as the Mirasol or the Mirasol effect. The Mirasol effect. Now this butterfly has got this beautiful blue color. It is, but it does not have an ounce of the dye, blue colored dye. Look at the structure. See, this has been enlarged here. You look at the structure, it has these ridges and, it has this retinor wings. They are called as retinor wing. The structure of the wing is so. This is the cross section of the wing. It is so. So when light falls on this, when sunlight falls on this, it gives this blue color. And that is how this Mirasol effect. So let's see a small video on this. Just a minute. Can you see the video? Can you hear the video?
Yes, madam.
Yes, madam. Yes.
Oh.
Yeah.
Go back then, all that it would take to actually get to this point, I think we would have been a lot more scared. It was very risky.
Madam, have you shared the computer audio?
Yeah, initially, madam, we could hear, but now it's not audible.
Yeah, ma'am. Perfect.
Okay, thank you.
If I knew back then all that it would take to actually get to this point, I think we would have been a lot more scared. It was very risky. I think technically it's a very risky thing to do because there aren't very many display technologies that actually make it. I mean, there are hundreds that have come and gone, and there's only a handful that actually make it in the mainstream.
We use mirrors to bounce light back. The question really was, did it make a good display?
I mean, we thought it was the most beautiful thing in the world. It had that shimmering, iridescent glow to it.
People often say, gee, it looks like it's glowing like butterfly wings.
In the same way that you see a butterfly's wings shimmer or a peacock feather shimmer, that concept is what sits behind every Mirasol display. So we're able to take the ambient light, it strikes this surface, and then we're able to choose how we modulate it and send it back.
It's a completely different way of making the color than other displays. It's completely different.
If you can mimic that, you've got a pretty compelling technology, not just from the value proposition, but think of the colors that you can generate based on that palette.
As we move forward in the world of biomimicry and we look for real avenues of change, we're looking for companies to design solutions that are based on nature's designs. The Mirasol display is an incredible example of how business industry can learn from nature. And then you're like, wow, nature is simple because nature is very energy efficient, and we can learn a lot more from nature with respect to energy efficiencies.
Anytime you can adopt and build on what nature has given us and put it in something that's in your hand, it gives you much lower power, sunlight viewability. How could you not be excited about that?
Okay, so this is how, this fabric, which I'm going to show you now, the Morphotex Fabric. This fabric is made by a Japanese firm, Teijin Limited, and it has nothing, no dye in it, but you can see the different shimmers and the colors which it shows, specifically the blue color of the Morpho butterfly. It has been, basically the concept has been taken from the butterfly. So chromogenic fiber Morphotex is the world's first optic coloring fiber. Now, if such fibers can be made and maybe in the next 15-20 years, then the dye industry, which is one of the most polluting industry, will be stopped, because we will get colors only due to the structure of the cloth. Okay, there's a lot of chemistry involved in this. But the best part is you don't have to have a dye pigment, you don't need a solvent, you don't need drying techniques, and you don't need, it's really amazing that a fiber like this is already there in the market. So the color is based on varying thickness and structure of the fibers and reduced energy consumption and chemical release by eliminating the dye process. So this is one very good, beautiful innovation which is come from green chemistry and biomimicry, that is mimicking the nature. So they have studied the nature and from there they have come to this, and this is actually going to reduce the energy consumption and the chemical release of the dye process. So in other fields like where green chemistry innovations which can take place is building materials, cleaning products, food products, garden and home, electronics, medicine, jewelry, cosmetics, you name it. And green chemistry is doing innovations in these fields. The green chemistry market has grown up, and you'll see right from 2015 where it was a $1.7 billion company to that chemistry. Today it is reached to $85.6 billion. So you can see that how it is growing. You can see this graph from 2011 to now. Today it's more than $100 billion company or industry, that is the green chemistry industry. What drives green chemistry? 25 years of progress, the future leading to a green and sustainable world. What will you invent? What can green chemistry do for your community? What role will you have in green chemistry? Do you already have a green chemistry innovation in mind? So yes, this is what drives green chemistry. That is one world, clean world and green world. We all are responsible for this, and we all being chemists, I think we should all, whether we are a chemist or a biologist or a technology, because the chemist can design and the technologies can be applied on various sectors in the industry to grow to a clean world and a green world for tomorrow. So let's address the 12 principles of green chemistry. What do they give? What are the benefits? The environment, products will be biodegradable and won't persist in the environment. To human health, products won't cause toxicity to humans. To the economy, novel products will boost competitiveness. For sustainability, products made from renewable resources, so it will be sustainable. And for science, fundamental new insights. Innovations is what will grow in, it'll make you think. Green chemistry makes you think, how can I do this differently? So that is the benefit. Again, green chemistry moves our consideration of how to deal with environment problems from the circumstantial to the intrinsic level. So molecular designs for reduced toxicity. So you just saw a molecular design of the Morphotex fiber, how molecular design has reduced toxicity, reduced ability to manifest hazards, inherent in, now like in the same fiber, it is reduced ability to manifest hazards, because we are not using anything hazardous like the dye, where we use mostly the azo dyes, or we use the phenols which are carcinogenic in nature. So we are totally removing that hazardous chemical from the picture, inherent safety for accidents or terrorism, increased potential profitability. So all these things. So what is the benefit? Hazards must be recognized as a flaw in the design process, and that is what is basically the benefit of green chemistry. According to green chemistry, risk is equal to hazards into exposure, and we are focusing on reducing the risk. So if you reduce the risk, obviously you will reduce the hazards. And that is how green chemistry is very, very beneficial to all of us. Let's take the green principles one at a time and case studies. All of us know this diagram. I think most of the textbooks have. This was put forth by Roger Sheldon in 1994. Industrial sectors and annual production and the annual waste produce. You see this, oil refineries. Annual production is 10⁶ tons. This is T means tons, and 10⁸ tons. Whereas the waste produced is nearly the same. Then bulk chemicals, you will see that the waste produced is more than the bulk chemical produced. Fine chemicals, again, you will see that. Pharmaceuticals also, the amount of the pharmaceutical product is less than the waste produced. So what are we doing? We are basically creating the waste, and then we are trying to, do the treatment to the waste, and we are spending more money on that and making the product costly, because waste treatment is something which is required, and we are also polluting the atmosphere. So the first principle is waste prevention. It is better to prevent waste than to treat or clean up waste after it is formed. So what does it say? Avoid the generation of waste. So you have to find alternatives to A and B to improve overall efficiency of a reaction. Incorporate better catalysts to push the reaction to full completion. Let's take this case study of sildenafil citrate, that is Viagra. Now, when Viagra was introduced, in a year's time, the sales of Viagra reached more than 1 billion. And therefore, obviously, the production of Viagra was large. It was a 11-step synthesis, which gave a 4.2% overall yield. You can imagine a 11-step synthesis giving you only 4% yield. And the waste, you can see here in 1990, 1,300 liters of waste was produced per kg of Viagra. You can imagine the amount of waste produced, 1,300 liters per kg, and today it is 7 liters per kg. So in the last, from 1990, in the last 30 years, the process has been over and over viewed, and then changes have been brought, and now the waste produced is 7 liters per kg, and in the next 5 years, it is predicted that the waste produced will not be more than 4 liters per kg, which is also huge, because what is the waste? The waste is all these solvents like methylene dichloride and acetone and methanol and ethyl acetate, butanone. You can see the number of solvents which have been used, because there are 11 steps. There are 11 steps, hydrogen peroxide and thionyl chloride. I mean, n number of solvents which are hazardous. But since the market value of Viagra is high, the production has not yet stopped, but they have improved on the production. So why, if 1,300 liters of waste was produced per kg, you can imagine how much of waste management was done in 1990s, and now it is only 7 liters per kg. So you can imagine then that the cost has come down, the waste prevention cost has come down, and even the pollution in the environment has come down, because the amount of waste has gone down so much. So this is again the same thing, alternative procedure of sildenafil citrate. The yield in the last 3 steps is 97% now, instead of the 4.2%. And the solvent, as I told you, has gone down from 1,300 liters to 7 liters, and only the solvent tertiary butanol, ethyl acetate and 2-butanol are found, and traces of toluene are used. All other solvents have been scrapped off. The number of solvents which you see here, I mean, you can see the number of solvents 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In 11 different steps, 11 different solvents were used, and now only 3 solvents are used. So you can see that the future target is even to reduce these solvents. Reduce these solvents because these solvents are also hazardous. Okay, the storage of, they are all volatile. Organic solvents are mostly volatile. So because they are all volatile, so it has to be controlled. Then second is phenols. The synthesis of phenols. Now initially phenols were obtained from petroleum, which is obviously a depleting source. Petroleum products are all fossil fuels. The method is not sustainable. It depends on depleting resources. But today's alternate method, production of phenols from biomass, waste using the depolymerization. So this is biomass and catalyst hydrogen gas. And what you get different types of phenols. So obviously now we are using a renewable source, the biomass. This is what you're going to use using the technique of depolymerization. So, you know, these are some of the, I should say, the synthesis which has occurred using the principles of green chemistry. Then waste prevention again, production of ethylene oxide. Now, ethylene oxide is a very important industrial chemical because it is used in many industries to prepare ethylene glycol. It's used to make use as a fumigant in certain agriculture product and as a sterilant for medical equipments and supplies. And therefore, initially there was a two-stage synthesis in which chlorine gas was used with water. Cl2 plus water. It was a two-step synthesis to make ethylene oxide. But today, the new synthesis is 100% atom efficient synthesis where you know, only air is used in presence of silver catalyst at 200 degrees, and what you get, so ethylene plus air, and the new process generates 16 times less waste than the original one, and it eliminates the formation of wastewater which contained the lot of chlorine. The E factor for this particular reaction is 0.3, which is supposed to be very good. Okay, so this is another example of waste prevention. Then we come to the second principle, that is atom economy. So synthetic method should be designed to maximize the incorporation of all materials used in the process into the final product. Ideally, all atoms from the reagents are incorporated into the final product, and therefore less waste will be produced. Let's see an example of this. Epoxidation of styrene. Now styrene is, all of us know, polystyrene is used in a number of things, and this process, epoxidation of styrene, only 23% of atom economy was there because 77% of the product which was formed was a waste. 77% of the product was this metachlorobenzoic acid, which was not the desired product. The product which was desired was only 23%, and therefore we are producing 77% of the waste. So it's a, as I told you, polystyrene is very useful. It is a very useful plastic. It scales in production being billions, several million tons per year. Now alternate procedure, how to make styrene. The conventional method to make styrene was from benzene. Again, benzene is a petroleum product and is carcinogenic. And now what they are doing is they are using something. Give me just 1 second. You know what is Diel-Alder's reaction? A diene and a dienophile will give you a adduct. Okay, so this is Diel-Alder's reaction. And the product is 100% atom economy because all the starting material here, which is butadiene, 1,3-butadiene, is getting converted into the product. There is no byproduct which is formed, and therefore This is the best method for synthesizing styrene, which is used for the synthesis of polystyrene, a widely used plastic. Brufen, all of us know, traditional method, 6 stoichiometric steps and less than 40% atom utilization. The yield was very, very less. The byproducts were more. And today, the green chemistry, there are 3 steps. The number of steps have reduced from 6 to 3. And 80% atom utilization is there in the product. And if you take acetic acid, which is a byproduct of the reaction, then 99% of the atoms are recovered, and therefore only 1% of waste is produced. All the atoms which are there in the starting material are now incorporated either in the product or in the byproduct, that is acetic acid, which can be easily separated and used for different industry. That is the second principle of atom economy. So when we design a synthesis, we should design the method in such a way that all the atoms can be incorporated. Then the third principle is less hazardous chemical synthesis. Whenever practicable, synthetic methodologies should be designed to use and generate substances that possess little or no toxicity to human health and environment. Now, in the toolbox of an organic chemist, there has been, many new reactions have been developed, innovative reactions which are the work of the green chemist. So, cascade or tandem reactions such as the CH activation, metathesis, and enzymatic reactions are some excellent examples of the cleaner and more efficient scientific tools that are now available to organic chemists. And therefore, this cascade reactions means continuous reactions. You don't have to separate anything from the intermediates are not separated, so you don't waste anything. The reaction continues and you get the product. So they are very good. Again, let's see the very classical example of adipic acid, which is hexane dioic acid, which is one of the most produced commodity chemical worldwide because it's used for making nylon 6,6, as well as it is used in many other chemical industry, pharmaceutical and food industry. Benzene, it was initially the conventional process. Benzene was used as which is a carcinogenic as a starting material to give adipic acid, and nitric acid was used, which involves for the oxidation. Excess of nitric acid was used, which was again giving out a greenhouse gas called as nitrous oxide, and therefore this method was not a very good method. The alternate method is now you start with glucose. So benzene again, which is obtained from non-renewable resource, is replaced with the renewable resource, that is glucose, and then we are using a biocatalyst which is converting glucose into adipic acid, and this is a very, so we are using less hazardous chemicals, and in the starting material is less hazardous. The reagents which are used, the bioenzyme is less hazardous, and therefore this process had won the prize, EPA Presidential Award also. Then design safer chemicals. This is the next principle. Chemical products should be designed to preserve efficiency of the function while reducing toxicity. That is, everything is toxic. It simply depends on the dose, often otherwise phrased as the dose makes the poison. So we know this, that chemicals are basically poisons. Only we should design it in such a way that in small doses it should show high efficiency, and therefore it will not be poisonous, and once it has finished its work, it should be degraded very easily. If it doesn't degrade, then obviously it's going to show the side effects. Okay, so that is how. So the types of properties which we are going to see, or which we are going to consider for designing safer chemicals, these are the properties. I will not go into the details because I think yeah, we have half an hour left, so let us just see the properties. Chemists can design chemicals which have reduced toxicity by manipulation of chemical bonds. As I told you, chemists are very good at manipulating chemical bonds and chemical functional groups. The only thing here is that we have to have a good knowledge of fundamentals of chemistry. Reactive functional groups have a great potential to be toxic. Removing these groups is like to reduce toxicity. So we should know which groups are reactive and which are not, and why which group should be kept and which group should be removed from the molecule so that the toxicity levels go down. Elimination of molecular initiating events that activates pathways, while difficult to achieve if the chemical is modified not to interact with the biological pathway. But this is very difficult because most of the chemicals, when they enter into your body, they do interfere with your biological pathways, maybe till the drug is there in your system. And therefore, to make a drug which will totally not interfere with your biological pathway is, as of today, not very possible, not very feasible. Reduction of eliminating bioavailability. If a chemical does not absorb into a body, it cannot cause harm. So, if the chemical is not biodegradable, then it should be such that it does not enter into any living system. And if it is not going to enter into any living system, so the design should be such. You should make it in such a way that it taking all these points into consideration. Like for example, now we spoke about DDT. So DDT was an agricultural pesticide and it was also used to control malaria, but it is carcinogenic, and the threat to wildlife, especially birds, had almost led to the extinction of a bald eagle population because the eggs, you can see how the shells were thinned by DDT. Now, instead of DDT, after the ban, a new chemical, a new pesticide, spinosad, for insect control has come into the market. It is produced by the bacteria Saccharophyllospora spinora. Isolated from Caribbean soil sample, sugar mills. It is selectively it targets the nervous system of the insects and has got very low mammalian toxicity and a good environmental profile. So such chemicals, such pesticides are useful because on mammals it is not going to show much effect like DDT, and therefore now this is the pesticide which has replaced DDT. So it's obtained from this bacteria. Then halogen-free firefighting foam. Now Solvents company has come forth with a firefighting firefighting foam called as the rehealing foam. The firefighting foams, which they usually contain a lot of halogenated fluorine surfactants, and that is why, once these foams are there, then a lot of fluorine is around and it has a very negative impact on the environment. So this foam is a blend of non-fluorinated surfactants and sugar, which is now into the market. This has less environmental impact and it shows excellent performance on control of fire and backburn resistance, which is of paramount importance to the firefighters. It does not burn back, so it's really a very good foam, and also achieves full regulatory compliance with the existing fire protocol. So this particular foam is now in the market and is being used. It was innovated by Solvents company in 2014. Then the next is safer solvents and auxiliaries. As we all know that most of the reactions, 99% of the reactions are carried out in solvents, and then there are separating agents, etc., which are used. Now such solvents and separating agents and all are not very safe. They are actually not very safe. And what do you do with the solvent? Once the reaction is completed, what do you do with the solvent? Because we are not talking about our chemistry lab or your small labs. We are talking about industry, and they use solvents in tons. So the waste produced is huge. And where does it go? Either into the water body or into the landfills. And they are all, most of these solvents, especially the organic solvents, they are toxic, they are flammable, corrosive, volatile. So, you know, storage also becomes a big problem. And they pollute, because they are volatile, they pollute the air, because they, you know, they pollute the water, because they are either thrown ultimately end of the pipeline, they go into the sea or into any water bodies or into the land, and creating a lot of pollution. They also risk the exposure can lead to a huge accidents. So therefore, if we can have safer solvents and auxiliaries, or if we don't use solvents at all, solid phase synthesis, then the problem can be solved. So these are the areas like avoidance. No solvent you can use, good, and the green alternatives are such environmentally benign and safe, that is water can be used as a solvent, because that's not going to pollute either the water bodies or the atmosphere or the landfills. Then easily separable, safe supercritical fluids like supercritical carbon dioxide, and zero volatility, that is ionic liquids. These are some of the possible greener alternatives given by the green chemistry, or they are recommended by the green chemist. So let's see a case study, caffeination, decaffeination of coffee. Now, initially in the conventional method, dichloromethane was used, which now dichloromethane we all know is volatile, and it's not a very safe solvent, and it can lead to headaches, mental confusion, nausea, vomiting, dizziness, and fatigue. So we're not talking about the people, but we are talking about the people who are working in the decaffeination industry, where they are working and they are decaffeinating coffee there. So today, this dichloromethane has been replaced by supercritical carbon dioxide. So what they do is they take the coffee beans, they soak it in water for 5 to 6 hours, and then the soaked beans are taken into this absorber. They are taken into this processor. In the processor, they pass supercritical carbon dioxide at 90 degrees and 250 atmosphere pressure for 5 hours. Then the decaffeinated beans are removed and dried and roasted, and you get your coffee, which is decaffeinated. The dissolved caffeine is transferred to the recovery chamber, and from the recovery chamber, what they are doing, the caffeine is dissolved in water, so it is leached out of the supercritical carbon dioxide, and then this is sold to the soft drink manufacturers. They make those all energy drinks like your Cloud9 and I don't know what else, what other drinks are there. So all these energy drinks which are made, Pepsi ka bhi ek hai, that Pepsi Sting and so on and so forth. So it is passed on to those companies, and purified carbon dioxide is recirculated. So here you're using the solvent and then you're recirculating, you're using the same solvent again. So what are you doing? You have cut the step of using a volatile, toxic, organic solvent, dichloromethane. And instead of that, you're using supercritical carbon dioxide, which is already present in the atmosphere, and it is reusable. And this is how safer solvents and auxiliaries can be done. In chromatography also, today dichloromethane has been replaced totally. It can be replaced by 5% DCM and methanol, or it can be, so you can see the chart which shows different solvents which can be used. 60%, and that is 3:1 ethyl acetate plus ethanol, and isopropyl alcohol can be used, and so on and so forth. So instead of using dichloromethane, which is toxic and hazardous, we can use those solvents which are less toxic and more safer as compared to dichloromethane. Then this is manufacturing for sertraline. Sertraline is a top-selling antidepressant drug. The conventional synthesis was a 3-step process, and it used 4 hazardous solvents: methylene chloride, tetrahydrofuran, toluene, and hexane. So that was in the conventional process. Today, they have streamlined the process, and it is a single-step process which is carried out in ethanol, which is much less toxic and toxic solvent. Ethanol, all of us know, is comparatively very less toxic. New process is also catalytic, cutting down on starting material by 60%, 45% and 20% for the 3 components of the reaction. So you can imagine that the starting material percentage has also gone down, the use of hazardous solvents has also gone down, and in the combined steps eliminated 31,000 pounds of titanium chloride in the initial process. But today that has been scrapped off. 22,000 pounds of 50% sodium hydroxide, that is also removed today, and 33,000 pounds of 35% hydrochloric acid waste. So much of waste, around 1,000 pounds of waste is not produced anymore in this particular antidepressant drug which is there in the market and which is developed by Pfizer. Then design for energy efficiency. Energy requirements should be recognized from their environmental and economical impacts and should be minimized. Synthetic methods should be conducted at ambient temperatures and pressures. So if you really observe in the industry, most of the heating, cooling, separation, pumping is done for what, it's done for shifting the material from one place to another and all those things. Most of the reactions can be carried out at ambient temperatures and atmospheric pressure in order to minimize energy usage. So atorvastatin, we all know it is used. It's a statin which is used by all to lower the cholesterol. So it is an energy demanding synthesis. The original synthesis is an energy demanding synthesis, and it had 2 cryogenic reactions at -70 degrees Celsius. The new method, which is a biocatalytic synthesis, it uses the enzyme 2-deoxy-D-ribose 5-phosphate aldolase, that is DERA, and shortens the process by removing 2 energy intensive chemical steps. So obviously the energy efficiency of the reaction has gone up, the number of steps have been reduced, and total efficiency of the product has also gone up. This is a very useful drug because it's used very commonly by all patients who are cardiac patients as well as high blood pressure, etc. I'm sure all of you know about it. It's a statin. Then we can use different energy methods like the sonochemistry or the microwave chemistry or photo-assisted reactions. Now all these reactions, sonochemistry, all of us know that use of high frequency sound waves to promote a chemical reaction, and the collapse of bubble formation in the solution generates a very high temperature and a high pressure than conventional heating. It is used in the production of triglycerides from methyl transfer esterification. Microwave, everybody knows because it's a high frequency electric field and it can be used for heating or cooling the environment with electrical charges, and it aligns the reaction, the pace of the time of the reaction also becomes less. For example, the simple aldol condensation, which usually takes 2 hours, when done in a microwave, the same reaction is completed in 3 minutes. So you can see the difference in time, 2 hours and 3 minutes. Even in microwave, even the solvents which are used, the amount of solvent which is used goes down, and it's very energy efficient, and the reaction takes place in a very short time. So microwave reactions are also very important and very good reactions, but industry has still not made such a big microwave. But at the initial levels, a lot of research is going on. Photo-assisted reactions naturally occurring, such as using the sun as a catalyst. used in photo-driven acylation from the production of valuable synthetic intermediates and commercial fragrances in bulk. So many like BASF, which is it deals in most of the chemicals. It's the one of the biggest chemical industry. It has developed automotive premier coating, a precursor which is already able to be cross-linked under photo eradication as opposed to its conventional energy initiative thermal driven variation. So BASF anyways is into many innovations, more than 20 innovations. It is into the chemical circular economy type of innovations which is taking place. I'll explain it in short a little later. Then use of renewable feedstocks. So no raw materials. All of us know that if the feedstocks are not renewable, then if they are depleting, then after some time the process is not sustainable because you are not going to get the starting material. So today, initially we were using petroleum products, that is hydrocarbons, and they were converted into olefins, alkyl chlorides, etc., which were then converted into highly functional molecules. Now we can start with biomaterial like carbohydrates, proteins, lipids, which are already highly functional molecules, and they can be easily converted into highly functionalized molecules. So renewable feedstock is very important. So you can see here that biomass production in nature, 180 billion metric tons per year is the biomass production in nature. Only about 4% is utilized by humans, and so we can use them. You can see here carbohydrates, which is a very huge chunk in this pie chart. Building blocks for diverse chemical platforms. Lignins we can use for nature's richest source of aromatic carbons. Used in polymers, adhesives, production of phenolic chemicals, etc. And fats, that is proteins, terpenes, etc., converted into polymers, lubricants, and detergents. So nearly everything can be synthesized by using renewable feedstocks. Only thing is we need to think and innovate. This is a process producing polymer from renewable sources, that is the PHAs, which are now use instead of PET polymer, the PHAs. So you are using enzyme, polymeric substance, bacteria, sugar or other nutrients can be added to this, and the PHA is finally made. So this is the process. You take the food waste, so it is generated from waste, do some pre-treatment, enzymatic hydrolysis, fermentation, separation, harvesting PHA rich biomass, then centrifuge to collect the biomass, dry the PHA rich biomass and recovery, and then the raw PHA granulated, formulated into the and sold into the market. So you can see that from waste product also we can make this useful polymer PHA, and then why waste and use the petroleum products and then make polymers which are non-degradable, non-biodegradable, etc. Because this is a polymer which is biodegradable also. Similarly, this PHA, that is polyhydroxy alkonates PHAs, they are used for making your credit cards and all, and these credit cards are all biodegradable. So let's have more attention paid to such polymers, because polymers is something which gives rise to plastics, and that's a hue and cry that we should not use plastics, but obviously biodegradable plastics like this can be easily used. Then development of commercialization of toners. We all know that it's a very big industry, $4.5 billion industry, cartridge industry, and if you use this cartridge, then recycling of paper becomes very difficult, because the cartridge, the print on the paper, it's difficult to remove the print from the paper. But if you use a cartridge which is developed by using cornstarch, then it can be easily removed, and then once it is easily removed, the paper can be easily recycled. And now the alternate process. The first thing is that you can use biomass, that is again starch. You can use starch. So from corn you can make this toners, and you can use it so that paper recycling becomes easier. This is production of levulinic acid, which is widely used as a precursor for pharmaceuticals, plasticizers, and various other additives. Conventionally, a number of steps were involved. Hexose, glucose, fructose, or starch in dilute hydrochloric or sulfuric acid was used, and then the yield was dependent on the acid concentration, temperature, and pressure. So no constant yield was there, and a mixture of formic acid and levulic acid was what was obtained. The alternate process, that is the green process, levulic acid can be obtained from paper mill sludge, agriculture residue, waste, wood. So now what we are observing here is renewable feedstock. Not only the new, you can use the waste. The agriculture waste can be used. The paper mill sludge can be used. Waste wood can be used. So what we are doing, we are not filling it in the landfills, and but we are using it as a starting material for some other reaction, and that is what is called as circular economy. What is circular economy? Recycle, reduce, and reuse. So what are you doing? From one waste you're producing another product, and when that product goes to waste you produce another product, and so on and so forth. It becomes a circular economy. You're using less resources, and your economy, your money wise, you're becoming richer because you don't need to dig the resources. Okay, so municipal solid waste and waste paper, you can see what all can be used. Paper mill sludge utilization utilizes a high temperature dilute acid hydrolysis process that converts cellulose biomass into levulic acid. So you get only one product and you're using waste. So this is a very good green synthesis of levulic acid. And the company which has come with this is Biofine Inc. Now, reduced derivatization. We all know that we do a lot of derivatization. We're doing a reaction. We don't want the amino group to undergo any reaction. So what we do is we do acetylation, convert, and then we do deacetylation, and so on and so forth. So many reactions, protecting and deprotecting group reactions, blocking groups we are doing. But first thing is that it increases the number of steps, and second thing is that unnecessarily we are doing that because we can use something. So what conventional approach was substrate, you get intermediate A, then you get intermediate B, then you get C, D, and the product. So obviously if there are so many steps involved, then the product, the atom economy of the product, the yield of the product, everything goes down, and a lot of waste is produced in the conventional approach. Now the green chemistry approach is from the substrate you should directly get the product, no intermediate steps, and they've been successful in making. If you see this conventional synthesis, 6-amino penicillinic acid that uses 3 steps and intermediate products are formed. So you can see this synthesis that uses, and now alternate synthesis which uses enzyme and fewer derivatives. So only 1-step process, very few derivatives, nothing, and you get the final product. So this is how green chemistry is playing a very important role in chemistry today. Catalyst, we all know that catalyst plays a very important role because it lowers the energy of activation, and it controls the site of reaction, reduces the temperature necessary to achieve a reaction, and so on and so forth. So catalysis, there are many different catalysts, homogeneous versus heterogeneous catalysts. So there are green catalysts, readily regenerated and recycled, readily separated, long service life, very high rate, robust to poisons. high selectivity and mild conditions. These are the characteristics of green catalyst. So you have heterogeneous catalyst, you have homogeneous catalyst, and the green catalyst should have these characteristics. The homogeneous catalyst should have these characteristics. So let's take the example of polyoxometallate catalyst, which is a ligand, basically a non-toxic inorganic cluster compound. Selectively delignifies wood, utilizes only air and water, allows the use of oxygen instead of chlorine as the whitener of paper pulp and water as a solvent, generates only carbon dioxide and water instead of chlorinated organics. So you can see that this is the initial stage of making the water, the pulp, paper pulp, second step, third step. So you're eliminating the use of chlorine, which is used to bleach the paper to white. You can see at the end of the fourth step, when you're using this particular catalyst, the paper pulp is absolutely white in color, and you have eliminated the use of chlorine, and water is used as a solvent in this particular. And you can pass air because oxygen is used, so you can pass air, and therefore you're using something which is non-hazardous and which can give you good products. This is again a green synthesis of naproxene, naproxene, which is a non-steroidal anti-inflammatory drug of the propionic acid class that release. Okay, so here you can see that a chiral catalyst is used in the last step to give you 97% yield of S-naproxene, because the S enantiomer is the one which is active, and that is why the chiral catalyst is used here to get enantiomeric excess of one of the product, which is basically required and not a racemic mixture of the product. This is sitagliptin, which is all of us know used in the treatment of diabetes, type 2 diabetes. So they have developed the green synthesis by introducing a new catalyst. Obviously, these catalyst names and everything is not very clear, and how much they are using and all, because they are all patented products. But tetraamide macrocyclic ligand, a green catalyst for the treatment of pharmaceutical chemical residue with the potential to reduce the pharmaceutical industry's environmental impact. This is another, catalyst which is used. Now this catalyst can, they can react and break down the chemicals at the sewage treatment at the end of the pipeline. Like the breakdown of variety of chemical residues including that is Liptor, Prozac, Zoloft, the contraceptive pills and more, because otherwise all this end of the pipe products, they go into the water bodies or into the landfills, and they are very dangerous for the animal life. So that is why before they enter into the environment, this particular green catalyst is used, and these are the chemicals are broken down so that when they are thrown into the environment, into the water bodies or into the land spaces, then the side effects are not seen due to these drugs. So design for degradation. So we all know that chemical products should be designed so that at the end of their life or their function, they do not persist in the environment and instead break down into innocuous degradation products. Like in alkyl benzene sulfonate, sulfonated detergents were used earlier, alkyl benzene sulfonate, 1950s and 16s. Foam in sewage plants, rivers and streams. That is what was caused because of it. Persistence was due to long alkyl chains, and introduction of an alkene group into the chain increased degradation. So this is what is done, that introduction of an alkene group was done into the side chain, and they saw that the degradation was increased, and the problem of forming foam in the sewage plant or in the rivers or in the streams was brought down. Chlorofluorocarbons, we all know they don't break down, and they contribute to the ozone layer depletion. So something has to be done for these also. Now new products are coming in which are replacing, which have already replaced chlorofluorocarbons. And DDT, we know that the design of DDT was such that bioaccumulation, and it caused thinning of the eggshells, etc., etc. Even after banning for 50 years, it is still present in the soil. So you can imagine that the biodegradation of DDT was so bad, it takes a very, very long time. Plasticizers, we all know what are plasticizers. They are added to the plastics, and they improve the quality of the plastics. So this one plasticizer, that is diisononyl phthalate. They are basically all phthalate derivatives. This has been linked to liver toxicity, endocrine disruption, and carcinogenicity. So this was the conventional plasticizers. So today what they have done, they are using isosorbate diester, which can be derived from starch. So instead of using this phthalate plasticizer, they are now using plasticizers which are obtained from starch. They are biodegradable, and they are thermally also stable. They are thermally stable and biodegradable, so they can be used instead of using the phthalate plasticizers. Then PET bottles, we all know it remains in the environment for a very long time, and is made for depleting sources, because the starting material of PET is obtained from petroleum, and therefore the conventional plastics are now replaced by PLAs, that is polylactic acid. This polylactic acid has the properties which is similar to PET, but it is, the starting material is starch. So again, you can use biomass, and which is converted by using enzyme into lactic acid, followed by polymerization, giving you polylactic acid, and it can be readily hydrolyzed into lactic acid for recycling back. So once the use is over, it can be then readily hydrolyzed to give you lactic acid back, and that is why now this is the replacement which they have found for PET bottles. The real-time analysis for pollution prevention is basically, we use analytical methods to be further developed to allow for real life in process monitoring and control prior to the formation of hazardous substances. So when a reaction is going on, we should keep checking for the completion of reaction, and what type of waste is produced and how much time and energy is required for the reaction. So this can, analytical chemistry has been at the heart of environmental movement since its inception, because it is used to identify, monitor, measure, characterize all the way throughout the reactions, the starting material, the products, and what is happening, what is the actual time required. So all the instruments which we use are very, very important, and they can be used to analyze real-time processes. Green chemistry is applicable to all chemical processes, including the methods, protocols, and process of environment analytical chemistry. So these are some of the real-time analysis for pollution, that is the HPLC, solid state extraction and micro extractions, X-ray fluorescence detectors for multiple metal matrix, and supercritical fluid extractors, and so on and so forth. You have a number of instruments which can be used for real-time analysis and for pollution prevention. Let's look at this process is to minimize waste generation through the use of real-time in-process monitors, sensors, etc. Pollution and hazardous waste generated can be prevented rather than simply measured after it is produced. So solid acid catalyzed 1-butene isobutane alkylation process replaces hydrogen fluoride and H2SO4 catalyst. Process utilizes supercritical carbon dioxide to prevent coke accumulation in pores of solid catalyst, and online GC analysis can be easily done. So we can easily find out an exact time and so we are removing the pollutants and we are using supercritical carbon dioxide, which can be again reused in the process. Okay, then the different types of reactors which can be used are the flow reactors, the continuous flow reactors, which replace the batch reactors on large, medium and even small scale, have distinct advantages. The advantages of continuous flow reactors are precise control of reaction conditions, reproducible reaction outcome, and minimum waste, and provides increased safety. This is a real-time analysis of a cooling system. In the conventional cooling systems, large amount of water is required because it's a cooling system. Microbial growth and mineral scale decreases the efficiency and increases the energy consumption of the heat exchanger. However, high level of this, biocides to prevent microbial growth inside the risk, which increases the risk of leakage in the system, is used. Means high level of biocides are used to prevent microbial growth, and the biocides and metal byproducts for corrosion are then released into the environment. So conventionally, this cooling system is polluting the environment because it's putting in biocides, and it is also giving throwing the metals which are formed due to corrosion in this system. Now this is a APO greener reaction condition award procedure, which is the alternate cooling system with 3D TRESA technology. So this in 2008 has NACLO company has got this award, and this is the site where you can read more about it. So what they did, the 3D this system allows for real-time monitoring of mineral scale buildup in the system. The system can also use poor quality water, not necessary that it should use very good quality water. 3D scale control prevents mineral scale formation to increase efficiency. So if mineral scales are not formed, obviously there will be no scaling and there will be no corrosion. It will take place at a very low rate. Biocontrol performers a real-time check for planktons and sessile bacteria. So there is a biocontrol in the system. It helps to check on the growth of the bacteria, so that the heat exchange is proper and everything, the reaction takes place, the exchange of heat takes place, or the cooling takes place properly. This residue reduces the amount of biocides used, since biocides are then added only when necessary rather than on a set schedule. The 3D TRESA system greatly reduces the amount of wastewater discharge from cooling systems. So that is why this technology was given EPA Green Reaction Condition Award in 2008. Now the last principle, inherently safer chemistry for accident prevention. Substance and form of a substance used in a chemical process should be chosen so as to minimize the potential for chemical accidents, including releases, explosions and fires. Accidents can be avoided by minimizing hazards. So basically, in this case, the approach to design safer chemistry can include the use of solid or low vapor pressure substances in place of volatile liquids. And other approach includes avoiding the use of molar halogens in large quantities. Continuous flow process can help to minimize chemical hazards. So we know, because if the chemical is volatile, or if it is it can inflammable, most of them are inflammable, then a lot of, and you keep on changing the reactors, vessels, then also it becomes a problem. So basically now this is a very good example. This is the PHA. These seats in the aeroplane are made up of PHA, and PHA, when it is heated at 180 to 200 degrees, it gets converted to polybenzoxio, that is PBO. and water as a byproduct. And this PBO is fire resistant. So if something goes wrong with the aeroplane, these seats are very safe. So, they are designed for safer, so that accidents can be curbed or reduced. So such designs are now into the market. Again, you can see here, this is a typical synthesis of pyrimidone, dihydroxypyrimidone, which is a pharmaceutical compound that is a calcium channel blocker and antiviral, antibacterial, many activities it can show. And it has been synthesized since 1800s. But there are two routes in this. You can see the first route, catalysis, HCl 2 drops, solvent ethanol, temperature 80 degree, time is 3 years. So this is the first route to get the same compound, and the new route, the green route, is catalyst zinc chloride 25 moles %, and solvent is none. So without any solvent, temperature is again 70 to 80 degrees, and the time is 15 minutes. So obviously the second process, the second route is very good. It does not have any solvent like ethanol, which is inflammable, volatile. Here no solvent is there, and therefore, and the time requirement for the completion of the reaction is just 15 minutes, and therefore the second process now is the one which is most commonly used. If you want to see inherently safer chemicals for accident prevention, so you can go visit Presidential Green Chemistry Challenge winners, and all the awards for 25 years are here. So you can actually read them and see the different awards for the processes which have got these awards. Now, the second part of this green chemistry, can I take 10 more minutes?
Yeah, sure.
Okay. Yeah. So the biomimicry, that is nature versus the lab. So in nature, chemical transformation happens at ambient temperatures, whereas in the lab, chemical transformation happens at high temperature and high pressure. In nature, there is minimum wastage. We have a large amount of waste which is produced. Utilize water as a solvent and reagent. Nature uses water as a reagent. We utilize petroleum-based solvents, like we use benzene, dichloromethane, tetrahydrofuran, etc., hexane, and so on. Complex molecules seamlessly are formed in nature, and complex molecules take skills, specialized catalyst in lab. Domino and cascade reactions are the ones which are there in nature, and step-by-step reaction is what we do. Enzymes are the catalyst, and precious metals like palladium and platinum and silver is what we use as a catalyst. High selectivity in nature and moderate selectivity is what we have in our labs. So if we look at these things, we can always think that biomimicry is, as we have seen the example of those surface Morphotex fibers for colors. The surface chemistry of that fiber is very, very important, and it can show you colors without using any dye. So looking at nature, if we can develop chemistry. So designing an ideal green reaction, we have all this: generate no waste. These are all the points which we just read. So minimum energy should be required, high yield should be there. Then no solvent or environmental benign solvent should be used, and so on. And then we should use alternate starting materials, renewable resources. Waste as starting material is what is required for us to be used. So if you look at nature, then you will observe that this is what nature is doing. This is what it is not using anything. The byproduct of one reaction is used as the starting material of the other reaction, and that is how we should also think. And I think the process has started, but a lot has to be done still, and the coming generation will have to work a lot on this so that we make our process very sustainable. These are some of the solvent, alternate solvent medias. So the names of the solvents which can be used as green solvents are referred as preferred solvents. Then usable solvents and undesirable solvents, and most of the reactions, if you see, they have the undesirable solvents used. Microwave reactors for energy sources. So we can use microwave reactors. Sonochemistry can be used. Photochemistry can be used. Now microfluids. This is very interesting. These are, reactions at a femtoliter, very small amount, very small volume of fluids. So it's both the science which deals with the study of behavior of fluids through micro channels, and the technology of manufacturing micro miniature devices containing chambers and tunnels through which fluids flow or are confined. This is basically more used in life sciences, but obviously we also can use it. They are called as microfluidics, is another topic which needs a lot of attention. It's attracting a lot of attention, and it may be used in future. Advantages: fast reaction, increased mixing capability, low energy requirement, increased worker safety, and less workup procedures. And disadvantage: more upstream research time, can be time consuming to optimize reaction conditions because it's in femtoliters. Clogging in microchannels is also possible, and currently limited reactions are possible because it's just in the genesis state. Not much of reactions have been done in this particular field. Flow chemistry, all of us have heard about this, that we have this batch process. What is it? You take step 1, decant, purify, go to step 2, decant, purify, go to step 3, and then you get your product. So you have this batch system. Now in flow chemistry, what you do, you take the reagent A, reagent B, mix it in vessel A, then add something here, it goes directly to vessel 2, goes to the vessel 3, goes to vessel 4, whatever has to be added in between, and then you get the final product. There is no decanting, there is no, like in this process, decanting and purification, nothing. The process goes in a flow, and it allows chemistry to be automated. And the final product, it is found that the flow chemistry processes are much better, the reactors are much better, less contamination, less wastage, less energy, everything is required in flow chemistry reactors, and therefore these reactors are nowadays much into use by industry. Advantages: fast reaction time, increased mixing capability, low energy requirement, increased worker safety, and high purity, less workup procedures, because you're not going to do the workup after every step. You're directly going to do workup only at the final point, and that is why these are the advantages. As we know, biomimicry, as I've already explained, this is the science and art of emulating nature's best biological deals to solve human problems. The innovations which are already seen: thermal insulation, cool or heat building clothes, then remediate soil, self-assembling materials, prevent corrosion, prevent mineral buildup. So all these are, the information regarding all this is already available. A lot of information is available, and a lot of work is going on in biomimicry, and the work is done by chemists. So biologists and chemists are working together for this type of work. And the last thing which I would like to say is chemical circular economy. All materials around us, our furniture, computer screens, clothes, you name it, are mixture of different chemicals. So in a circular economy, what you do is you recycle. How we use, reuse, and dispose of the material, how we minimize waste, and how we make the most of the resources in that process. So that is what is circular economy, and this is the upcoming thing. Nowadays, industries like, big industries like BASF and other industries like Pfizer and all, they are working on circular economy so that, they can recycle. They're using the principle of reuse, recycle, and reduce. So what is reduced? The starting material is reduced because you're recycling your material and you're reusing, converting it into renewable form, something new, and that is how the circular, and it really pays a very high. BASF at present is having at least 20 projects which are under chemical circular economy. So if you go to the site and read, you will get those 20 projects which they are dealing with at present for chemical circular economy, and this is what is the future: green chemistry, biomimicry, and chemical circular economy. So we should be good in our basis of chemistry, but along with that we should also understand economics and we should also understand nature, so that together when we work we can actually come out with solutions to the problems which we are dealing with and build a sustainable society. So green chemistry in perspective: reagents, solvents and reactors, many considerations in creating a greener chemical product. Biomimicry, using nature as mentor and teachers to inspire new ways of creating greener, more benign products and processes. And circular economy: reuse, reduce and recycle. These are the references you can go through if you need. Thank you very much for your attention. Yeah.
Thank you very much
Thank you.
for that very enlightening talk. There is a proverb that we say that it takes a
Your
village to...
voice is echoing. Your voice is echoing. Is there any other instrument on?
No, ma'am.
Okay, fine. Now it's good.
Is it fine now?
Yeah, it's fine.
So there's a proverb that we say, it takes a village to raise a child. In the same manner, after seeing your entire presentation and listening to you, I felt like it takes a lot of thing even to, get something really, like small as a reaction. We may think in terms of lab, but there are so many other important considerations also. There are so many liabilities on us also as chemists to, incorporate the thought process not only in designing bioeffective molecules but also environmentally benign molecules. So it was really nice to hear you. Now I would request our chairperson, Dr. Archana Gurjar, to summarize the talk, and then we will open the session for Q&A.
Thank you, Zina. Madam has today taken us all on a voyage of green chemistry, all the principles and the case studies. So she started from the mission of green chemistry, and I agree with Madam that it's the need of our, as green chemistry is an integral part of our life. She explained the harmful effect of DDT and the alternative also. Then the global warming, the carbon footprints which are there, all sectors, the top 10 polluting industries. She spoke about the lead, the acid batteries which are giving the soil, the environmental hazard it is causing, the pollution. She has also, the wonderful thing she spoke about was structural colors, the Mirasol effect, that was worth the most greenest one which I liked the most. Then she has explained elaborately with various case studies all the 12 principles of green chemistry. She has covered all pharma, many examples from the pharma sector: Viagra, ibuprofen, sildenafil. Then she covered about the sertraline, the statins, the gliptins. Many pharma examples she took while explaining the 12 principles. Apart from that, as all industrial sectors are involved, so the food industry, the coffee decaffeination, the firefighting halogen-free foams, then the polymer industry, which we are using so much. And for that also, she gave very good greener alternatives for the adipic acid, the styrenes, and the PHAs, all the polymer industry also. And together with that, then how replacement of the PET bottles by PLA, then how real-time analysis can be used, and the current methods she stressed upon, that is the microfluidics and flow chemistry. And at present, the last point she summarized that the need of our green chemistry, the future, that is the biomimicry and the chemical circular economy to reuse, reduce and recycle should be the term which we should all take home, the take home message that we should imbibe these principles and try to use all our processes in the greener way. Thank you, Madam, for an elaborate explanation of all the 12 principles and the various strategies.
Thank you, ma'am. Thank you.
Yeah, thank you very much, madam, for giving us the time. And as a coordinator, on behalf of Kmkcp College of Pharmacy, I really thank you. Your information was so valuable that as a scientist, we should not only look for, synthesis of the chemicals, but it is our duty that whatever we manufacture or synthesis, it should be environmentally free. And we have no right to spoil our environment, our earth. So that was the key message which we have received, and you have very exhaustively and very nicely explained and given very interesting examples. And it was really so engaging session it was. Although it was a very, as said correctly by Archana madam, it was a voyage, but it was a very enjoying voyage of a green chemistry with you. Thank you very much for that.
Thank you, ma'am. Thank you very much.
Madam, with your kind permission, can we take few questions?
Yeah. Right.
So,
sure.
Dr. Vrish Dvaj has asked a question that what is the green process or substitute of lead battery used in transport vehicles and inverters?
As of now, I have not read anything. As of now, nothing, but I'm sure there must be, a lot of research going on, because green chemistry is just 25 years and, people are working towards it, but let's hope that the solution comes fast, because even e-waste, if we see, there's no solution, only recycling is the solution. So if we can find a solution of recycling the lead batteries, somehow that will be a good thing, because e-waste can be recycled very well. Now there are examples where this e-waste is used to make roads and construction of roads and all. So there are a lot of examples which are there where this e-waste is consumed and it doesn't go into the dump land. So some such solution I'm sure will come out, but as of now I am not aware of anything for lead batteries. Yeah.
Okay, thank you, madam. Dr. Vandana Panda from our own institute wishes to ask you a question on biodiesel. So, Hina, can you please unmute her so she can ask the question?
Kiran?
Yes.
Okay.
Hi, how are you?
Yeah, good. Okay. Now my question is about biodiesels.
Yeah.
Okay. Now, in what way are biodiesels green? Because number one, if I understand, they will burn and they will release particulate matter, which will contaminate the environment. Right? And two, are we not depleting plant resources? So whatever was green, we are depleting by using vegetable, those the plant-based oils, right, to generate biodiesels.
No, but you see, there are different ways. Biodiesel may not only the plants are used, there is waste also. Bio waste can also be used. So if waste is used, then obviously it's a recycling and method. And what you're talking about, anyways, any kind of fuel, if you're going to burn, there is going to be a carbon footprint left behind. So most of the processes are not using fresh plants; they are using the biomass, which is left. The agricultural biomass can be used to develop biodiesel. So I think that is a very good thing, because that comes into the circular economy. So the waste is used as a starting material. So
Okay.
that's
I've been
really
reading about use of these, plant-based oils as fuels. So I was asking from that point of view. And how
yeah.
many
There's a lot of research going on. There's a
Okay.
lot of research going on, but as on large scale, as on today, there's I think only the one biomass which is used. So which is basically an agricultural waste. So other methods are still, because everybody is searching for a renewable resource for diesel and petrol, because this petroleum is fossil fuel, and that is why a lot of research is going on in that field. If I get something, I'll 100% pass it on to you. 100%.
Definitely. Thank you. I'm interested. But are there any biodiesels on market?
Very few.
As you're
No,
saying?
I don't. I remember only one, if I'm not mistaken.
Okay.
But I'll confirm. I'll let you know. 100%.
Somehow I was surprised you didn't cover that aspect in your presentation, or maybe I missed it.
No, I was not on to biodiesels. I covered the other major problems in it. Yeah.
Right. But an excellent presentation. Really, you covered everything very nicely.
Thank you. Yeah.
Thank you.
Thank you, madam. Actually, I am. Anyone wishes to in the chat box, these questions were only there. So if anyone wishes to, we'll wait. Or I think you were very elaborate in your session, and actually you compared all examples with conventional and the greener approach. So this the session was very much explanatory, maybe probably.
Yeah, that's why they're rewriting their very nice session, very vital information, very informative session. Vandana madam has said a crisp and comprehensive PPT and talk.
Thank you.
So
Thank you.
a lot of reactions.
Actually, I have given my email ID. It's there on the last slide. So if anybody has any questions, you can ask me later also. Not a problem.
Thank you, madam.
Okay, thank you, madam. Anybody wants, or we can. Runal madam, what should we do?
So I'll just check if anybody has raised hand, then we can give a mic to them.
I wish this session was, in person, so there would have been much more good interaction. On platform and online platform, it's always, you can't see the people, and then it's always better to interact. So yeah. I wish
two-way communication is always
yes,
best.
always yes, 100%.
But your session was really nice, ma'am.
You have bridged the gap, madam, with a lot of examples.
Because our title is emerging trends, and what you showed us is really this is an emerging, requirement. This is what has to be done. I don't think there are now no more questions. Madam, thank you very much for your precious time and the knowledge you have delivered to us.
Thank you very much. Thank you, all of you. Thank you.
Thank you, madam.
Thank you.
The participants to please stay back. The eminent speakers today who contributed in extending our horizons of learning, Dr. Balchandra Bhandge sir, Mr. Pramod Daibate sir, Dr. Kiran Jatar madam. Further, I would like to thank all the chairpersons for today, Dr. Shrikant Ghorse, Mrs. Rupam Raut and Dr. Archana Gurjar. Apart from it, I would like to thank all the participants who were so enthusiastic and who were very, very patient with, all the elaborate sessions, asking questions and truly appreciating all the speakers, because that is what is also needed. It was a very enlightening session, and last but not the least, I would like to thank our Atal FDP coordinator, Dr. Mrunal Sanaye. Now I would request Dr. Mrunal Sanaye to brief you up about tomorrow's session, a bit about the.
I think all of you have attended 15 sessions. And now the time comes that you have to mentally relax. So we are arranging one session by Mr. Saurav Ghosh. He is a teacher from Art of Living, and he will be giving us the session Mind Matters, a session on stress management. That will be followed by a lunch, and then we will have a valedictory function. In valedictory function, your attendance will be appreciated to get your feedbacks about the Atal FDP, and that will be then followed with the assessment of your entire FDP, which will be conducted exactly at 3:15. How the link will be shared and how we are going to appear for the exam, that everything I will inform you tomorrow in the morning. So be there on time, and let's meet tomorrow because it's going to be a very important day as your assessment will be conducted. Thank you very much.
Fourth day of our Atal FDP program. We once again thank all the participants for staying tuned in with us, and we'll see you tomorrow at 9 a.m.
For a wonderful host who's hosting the session, and
My pleasure, ma'am.
so see you all tomorrow. Thank you.